Morning, everyone. Welcome to discussion number 10. Today, we're gonna cover some graphs and their implementations along with traversals, which I don't think you guys covered with Professor Aman. But before I go into presenting that, I just want to remind you that our lovely TA Andrew is organizing the Super Mario Bros. Movie watching, I guess. And he's gonna make sure that we get a discount. So anyone who wants to do that, there's a Slack channel for it specifically. We're still unsure of the date when exactly it's gonna be. It's either gonna be the day before the exam, so you guys can like unwind a little bit before, or we're gonna let you study that night and do it the week after that, but it's definitely gonna be one of the Tuesdays. So keep an eye on that, and the Slack channel will have all the details that you need. Now, I'm gonna move on to the actual topic of today's discussion, and that is going to be graphs. So we're going to cover properties of graphs, the representations of graphs that you will need, and then we're going to look at some searches and traversals real quick. And there are some practice questions that the TAs came up with, which I don't know if we'll get to them, but feel free to look at the slides afterwards and look at the question, because I'm pretty sure that this week we have a leak code style question for you guys with some real life application of graphs. So the properties of graphs. Graphs are data structures that consist of a finite set of vertices and edges. They're an unordered data structure, so that means we cannot we don't have the benefits of some potential searches to lower the complexity of it. But the important thing is that they have vertices, which store part of the data, and then we have the edges, which store the second part of the data in a graph, which would be like a path length connecting these two, if you want to think about it. The number of vertices is denoted by the absolute value of b, so that means that we're always going to have a positive value, and the number of edges is usually e, and once again absolute value, because obviously we cannot have a negative number of edges. That being said, I want to move on. Vertices in this graph are 1, 2, 3, 4, and 5, and then the edges are the lines connecting the vertices. So the line connecting 3 and 5 is one edge, 4 and 5 is one edge, 1 and 5 is one edge, 1 and 4 is another, and 1 and 2 is the last one. The number of vertices in this case is 5, sorry, 1, 2, 3, 4, 5, and then number of edges is also 5, 1, 2, 3, 4, 5. A path is a sequence of vertices with the property that each vertex in a sequence is adjacent to the vertex next to it. So a path is essentially like a sequence of vertices that are connected via a path, but they have to, they're connected via edges, but they have to be adjacent. So a path would be something like 3, 2, 1, and 4. And then you do have a path from 3 to 4, but it doesn't go directly from 3 to 4. It has to go down to 2 or 1 and then to 4. And a path is also 1 to 2, and 1 to 2 to 3, and then back to 1 and 4. All of those are paths. A simple path is a path that does not repeat vertices. So out of these three paths, we have these two, which are simple, and then the last one is not a simple path because it repeats, it visits vertex 1 twice. Directed graphs. So edges of a graph can have a direction. In directed graphs, you'll see something like, think about one-way streets on a map. If you have a one-way street that can lead from building 2 to building 1, you cannot go backwards. And that's the same with graphs. 1 cannot access 2, but 2 can access 1. And in general, when you think about graphs, think about maps, because that is usually how maps and like applications for maps are developed. Directed graphs are also called the digraphs for short. If you wanna create a path, you must follow the direction of the edges. And then, yeah, so you can think about undirected graphs as bridges, so you can go both ways, and directed graphs as slides, you can only go downwards. The directed graphs will always have the arrows in the diagrams. Yeah, Brody, that works too. Chutes and ladders, that works too. Directed graphs will always have the arrows. So if we do ask you a question, is this a directed graph or not? Watch out for that. Then the second property that we're going to talk about is connectivity. Two vertices are connected if there is a path between them, not necessarily just an edge, but a path. An undirected graph is a connected graph if all vertices are connected. So if we have a graph that looks something like this, we have a path going from 2, and it visits all the nodes. So we have 2, 1, 3, and 4, or 4, 3, 1, and 2. It's gonna visit all the nodes. Thus, it's a connected graph. A disconnected graph, we see that 2 does not connect to any of the other nodes, so we cannot have a path that visits it. Thus, it's a disconnected graph. Now we have a question: can a digraph, a directed graph, be connected? And the answer is yeah, because as long as you can have a path that follows, that can visit all of them. So if you look at this one right here, you have a path that goes from 2 to 1 to 3 to 4. It visited all the nodes. So it's connected. Now, another property is cycles in graphs. So cycles are graphs which contain, or cyclic or graphs which contain a path that starts with the same node and ends with the same node. So an acyclic graph has no cycles whatsoever. So if you think about this graph over here, we cannot have a path that starts with 1 and ends with 1, because 3 and 2 are not connected, 4 and 3 are not connected, and 4 and 2 are not connected. And you cannot do that starting with any of the vertices. If you think about, I think yes, you would have to have at least one cycle if you want to go back all the way. But I'm maybe not necessarily. I'm gonna have to check that for you guys. But moving on. A cyclic, but undirected graph, we have this little triangle here where no matter which one of these you start with, you can always come back to it in the same path. A directed graph that is acyclic, you have to be careful with these. So these three are connected, but you cannot go back to one once you leave one. So if you start at 1 and you go down to 3, you can go to 4, but from 4 you cannot go anywhere. So it's not, so you cannot really, it's not cyclic. And this one is also not connected either, because you cannot visit all vertices with these directions, because if you go to 2, then you cannot go anywhere else. If you go to 3 and then you have to go to 4, you're not visiting 2. And if you go to 4, this one, the second one, why is it cyclic? Because it has this cycle here, and undirected graphs, you can move anywhere from them. You don't have to follow a specific direction. So you can start with 1, go to 3, go to 4, and then you can go back to 1. You can start with 3, go to 4, go to 1, go to 3. You can go back to 1, to 4, and then to 3, and you're just moving in the cycles. Yeah, so in a directed graph, the arrows do matter. And you can only, yeah. No. As long as it has, as long as the graph has at least one cycle and it doesn't have to contain all the nodes, it just has to have some cycle, it's gonna be cyclic. And it has to involve more than 2 vertices, otherwise every undirected graph is cyclic. But the property to look for is if a graph is acyclic, because it's easier. You need to look at the nodes and see if there are no cycles, absolutely no cycles. Only then is it acyclic. And then the last graph that we have here is a cyclic but directed graph, which means that we have a cycle that goes from 1, and then you go to 3, and then you go to 4, and then you go back to 1. And you can do that starting with any of these 3 nodes. So if you start with 3, you can go to 4, to 1, and back to 3. So a cycle, a path that starts and ends with the same node, and does not have to visit all nodes, has to visit minimum of 3 nodes. So yeah, this is not a cycle because you have to follow the direction of the arrows when traversing the graph, and 4 cannot visit 1 because of the direction of the arrow. Trees are acyclic directed graphs if you want to make a connection back to previous data structures. Now, weighted graphs. Weighted graphs are graphs that have a value stored in the edges. So those values are called weights and are commonly understood as path lengths. So if you look at this 4 over here, it's essentially a length of getting some price that you have to pay to go from 1 to 2. Be it the length of the street that you have to walk, be it the toll that you have to pay for some booth. To connect 1 and 2, you have to go through this 4. You have to put down a 4 of something. So it's a value of some sort of price, some sort of sacrifice if you think about it. Because when you traverse a graph, you'll look at the algorithms starting next week of traversing and finding paths. And you're gonna look at the paths that have the least weight, because you don't want to travel a lot. So weighted graphs have values stored in edges. You can see them in the diagrams on the edges. Unweighted graphs do not have values stored in the edges, and thus unweighted graphs, all the edges have the same value in them. They have the same priority. Now, a poll question. I did not prepare a poll for you guys this week. I'm sorry, but I didn't really have much time to do that. So I'm just gonna ask you to type it out in the chat what answers you think are correct. Which of the following is true for the graph below? So is the graph acyclic, cyclic? Is it connected or not? Is it weighted or is it directed? Some good answers in the chat. I like the responses. So you guys are correct. It is C. It is a weighted graph. It is not connected because the 6 does not connect to anything. There, it has a cycle here, so it's not acyclic. It is not directed because we don't have the arrows, and we do have the weights, so it is weighted. Question number 2. What is the minimum number of edges in a connected graph with n vertices? Remember, connected graph has at least one path that connects all the vertices. So if you have n vertices, how many edges will you have? Start off with small numbers. Think about a graph with like 3 nodes. Yeah, good job. Great. That is the correct solution. So think about a graph with 4 instead of n vertices. And the least amount of edges that you need for a graph to be connected is if you have something like a little linked list, and you'll need 3 edges, which is 4 minus 1. So n minus 1 is the minimum number of edges. Now, graph representations. We can have a dense or a sparse graph. So a dense graph is a graph that has a lot of edges. So if you think about this one, it's easy to see why it's dense because all vertices are connected to each other. Like every vertex is connected to every other vertex. And this is, yes, Theodore. So it's, you have to think about like the number of edges with the proportion of vertices. In a dense graph, number of edges is going to be proportional to the number of vertices squared. And that's what you're going to use for problem solving later on. So think about this proportionality. In a sparse graph, you have very few edges. So the number of edges is going to be proportional linearly to the number of vertices. And these two properties will determine or influence what you choose to implement a graph, like what structure you use to implement a graph when you're programming it. So first implementation or representation is the adjacency list. So adjacency lists are really good for sparse graphs. So number of edges is significantly smaller than the vertices squared. And it essentially has a list of, it has it has like an array of linked lists of edges that are connected. So think about it, think about this graph, which is unweighted, cyclic, and undirected. And it's also a connected graph. So if you start with vertex 1 here, vertex 1 is connected to vertex 2 and vertex 5. And in an adjacency list, at the location 1, you're going to have like a little list of all the nodes that 1 is connected to. So 1 connects to 2 and to 5. So you have this list here of all the nodes that you can go to from 1. So these two nodes you can access from node 1. And you look at the location 2, 2 is connected to 3, 4, 5, and 1 directly. And we are only talking about direct connections, so there's an edge directly between them. So in this list at this location, 2 will have 1, 5, 3, and 4. So 1, 5, 3, and 4 can directly be accessed from 2. And then at 3, 3 is connected to 2 and 4 directly. We have 2 and 4 in the list, and so on and so on. You can use an array or a vector. It doesn't matter. It's just a list. It doesn't have to have an order. It's more about it doesn't have to have an order. You can create some form of like a priority queue with the edges so that the weights are, so a lower weight is prioritized more than a higher weight, but it really does not matter. You can just think about it of just think about it as a list, any list in any order of nodes that can be visited from a vertex. And the graph doesn't necessarily have to be connected. It's just that if the yeah, the last value, this slash here is just, it just means that there's nothing following it. It's just like a null terminator. But even if you have a disconnected graph, so suppose that these two connections don't exist, a 3 will just have like an empty list here. There just won't be anything in the list, and that's fine. It's a perfectly valid entry in the adjacency list. So no order is necessary within the list. The lists don't have to be linked lists. They can be vectors, arrays, whatever makes it easier for you to implement. In fact, I'm pretty sure I've seen all of it on project 2. And all you have to think about is the direct edge from these nodes to this node or vertex. So here's the little visual representation. This edge is represented by 1 and 5, or 5 being in the list at index 1. Operations, you can check the adjacent pairs. So if you think about, you want to see, is 5 adjacent to 1? So is there a direct edge between 5 and 1? You check if 5 is in the list at index 1. And that is gonna have the complexity O out degree of B. So out degree is something that's it's just a word for how many edges there are coming out of a vertex that you're looking at. So if you have vertex 1, the out degree of 1 is 2 because it has these 2 edges. But when you look at vertex 2, the out degree is 4 because it has these 4 edges here. In a directed graph, an out degree will be specifically the number of edges that go out of the node. So if you had an arrow, something like, or arrows, something like this, an out degree of 1 in this case would be 1 because there's only one path out of 1. This one is coming into 1. Does that make sense? We all good? Thumbs up in the chat. Or we're good on this. Yeah, indeed. That is actually, Jaden, the method that we advise you to use. It is some form of like hash table. So whatever type of hash table you want to use, you can use it, be it a map or a set or whatever. No, not necessarily. It depends on what kind of implementation you want to make. So if you want to have the output be sorted later on, or if you want to decrease the search time or something like that, you would want to have a sorted map or unordered or ordered map. If you don't care about the order, if you don't care about searching, you can, if you want to decrease the complexity of searching, use ordered. If you don't want to decrease the complexity of searching, you don't have to use an ordered map. So you can, the second operation on the adjacency list is seeing what neighbors each node has. So what nodes are adjacent to one, those are going to be all the nodes in the list. And once again, the complexity of that is the out degree of the vertex that you're looking at, in this case, one. Matrix representation. Matrix, Brody. So, okay, why a map would be better than a simple array? It depends on what you're trying to implement. So in this case, the values in our graph are integers, and this can be simply implemented with an array of arrays, right? But, or an array of vectors, better, because they can have different sizes. But suppose that you have strings stored as values in the nodes right here, a string. You might want a key there. It's going to be easier to traverse. It's going to be easier to find. It's going to be easier to locate and know what you're working with if you just put the straight up the string there. Yeah, okay, great. So adjacency matrices, they're used for dense graphs. So number of edges is proportional to the number of vertices squared. As opposed to the adjacency list, which represents only the edges that exist, adjacency matrix represents all possible edges. So if you look at this graph here, it's the same as the previous example. The matrix, and I hope you're all familiar with matrices, but matrices are like tables. And in that table, you put the number of, or all the vertices as for the columns and all the vertices for the rows. And then think about whether there's an edge going from the row vertex to the column vertex and vice versa. Well, for undirected graphs, it doesn't matter, but for directed, go from row to column. So graphs are fun things. And in this one, we think about is there an edge from 1 to 1? And in this case, there isn't. But in a graph, you could have something like this. It's a cycle going back to its own, like node going back to itself. And in that case, we would have a 1 here. If there isn't something like this here, we have a 0. So you got to watch for that too. But without that little cycle there is no edge going from 1 to 1. And then we think about, is there an edge going from 1 to 2? There is, we put a 1 there. Is there an edge going from 1 to 3? No. 4? No. 5? Yes. So this is the same thing. If you think about 2 and 5, it's the location at row 2, column 5, and row 5, column 2. So it's these two values are for that are for that edge. The thing about adjacency matrices and why we don't want you to use them for your project too, and I'm going to repeat this over and over again in office hours anyway, but I just want to let you guys know, is that think about a really sparse graph. Think about a graph that doesn't have this, this, or this connected, and maybe not even this edge here. You would have so many zeros, and they mean nothing. They're just wasting time. You have to store them somewhere. You're wasting that integer size memory location for a zero, for something that doesn't exist. So in those cases where the graph is sparse, where you don't have a lot of edges, you want to use a list, and you're going to want to use a list specifically for project 2. Now, operations on matrices. You can check adjacent pairs by directly accessing the location at row 1, column 5, or row 5, column 1 for undirected graphs. So if you want to see is 1 adjacent to 5, you look at this table that you have, which can be a 2D array or whatever you want to represent it as, and just check this specific location here for it. And in that case, if you have 2D arrays, because arrays in most programming languages have random access, the complexity is of 1. Getting the neighbors is a little more complex, I guess, where you're looking to see all the nodes that one is adjacent to. You have to traverse the row or the column of the node that you're looking for, and you have to check all of these to see which ones are 1, and then see what the neighbors of 1 are. So in that case, if you look at 1, for example, it has 2 edges. You have to check, does it have an edge to itself? No. Does it have an edge to 2? Yes. 3? No. 4? No. 5? Yes. It has 2 nodes that it's adjacent to, but it had to traverse through all the vertices to check it. So the complexity is O of V. So adjacency list versus adjacency matrix. Time for checking adjacency for adjacency list, out degree of the vertex. For checking neighbors, once again, out degree of the vertex. Can be much, much faster than the adjacency matrix if we have a sparse graph. The memory of it, so space complexity is number of vertices plus the number of edges. It's more space efficient than adjacency matrix if we have a sparse graph. And then if you have an adjacency matrix, the time complexity is of 1. It can be much, much faster than an adjacency list if we have a very dense graph. And checking the neighbors is O of V. The memory is V squared because you have V squared entries here. So if there's V vertices, you're going to have to put all of them on as rows and columns and have V squared entries. Time and memory trade-offs. So you have to really think about what kind of application you are building. So a sparse graph will obviously have an adjacency list as an implementation. A dense graph would have an matrix, and you really have to think about what you're building. So if you think about a map, so Google Maps, for example, there's a lot of streets going on. There is a lot of connections, a lot of edges, a lot of paths. So that would be like a dense graph, especially if you think about walking paths, for example, which is something that we have started getting in maps only recently. So in that case, you do want an adjacency matrix. You're going to have a lot of edges, and you're going to want to access them. You want to have that random access. But if you think about a sparse graph, so for example, building a web of, I don't know, website connections or a network of machines, you might not have that many edges um, as opposed to a map. Okay, so how to represent edges? You can represent them as a list, so of a list of ordered pairs, which contains both vertices that the edge connects. And I say ordered pairs because if you have a directed graph, the order does matter. So this type of representation is good for certain graph algorithms. So if you want to traverse the graphs, some of the algorithms will need you to represent the graph this way. So you just have a list of all the edges that exist. But it's not as commonly used as adjacency lists or matrices are. So if you look at our graph here, it's the same graph as before. Representing this graph with an adjacent or edge list, sorry, would be just listing all these edges. So edge 1 to 2, edge 1 to 5, edge 5 to 2, edge 4 to 5, edge 4 to 3, edge 4 to 2. And you can have 2 to 3, etc. It's just, this is just like an example. If you have a weighted graph, you can have triples in here instead of ordered pairs, where the last element would be the weight of the edge that you're representing. So here's the edge that we're representing. Operations on edge lists. Adjacent pairs is 1 adjacent to 5. Loop through the edge list to find 1, 2, or 1, 5, or 5, 1 pair. And that is the complexity is proportional to the number of edges. And then getting neighbors, what nodes are adjacent to 1, and then loop through the edges again to find all the edges that contain 1 in the pairs. Once again, it's going to be proportional to the number of edges because, as mentioned, we only represent edges in this list, and you have to loop through all of them. There is no shortcut for getting there. So this is too slow, especially for very dense graphs. So that's why matrices and adjacency matrices and adjacency lists are used more. Another poll: what is the time complexity of checking what vertex is adjacent to, or checking adjacency in an adjacency matrix representation? Quickly in the chat before I open the I think I've read that question wrong for you guys. But you are correct for that. That is correct. Now, what would be, and this is a really weirdly phrase, but what are all what's the complexity of checking what or all vertices that are adjacent to some vertex? That would be B, yeah. Correct. You're correct on both of them. So great. This is what they were looking for. So as the exam usually is, you're gonna have to pay a lot of attention to answer the questions correctly. So it is V, and if you were checking for adjacency, it is 1. So you were correct on both of those. This is too long of a question before I open the quiz for you guys. So I'm gonna do that first. And then We're going to go back to questions. So now,